28 million light-years from here, in a galaxy called the Whirlpool, there is a world about the size of Saturn that may be doing something no planet in our textbooks is supposed to do. It isn't orbiting a sun, it's circling a monster, most likely a black hole. And every so often, it passes in front of that black hole's blazing disk of superheated gas and blots the X-rays out completely, dropping them to zero for hours. In 2021, astronomers announced it as the first candidate planet ever found in another galaxy. And the object it orbits might be the first planet we've ever spotted circling a black hole. That sentence breaks something in your brain, and it should. A black hole is the place we're taught nothing survives, the cosmic drain that swallows light itself. So the idea that planets, ordinary-sounding worlds with surfaces and atmospheres, could be calmly orbiting one sounds like a contradiction. But not only is it possible, physicists now think there could be entire swarms of them. The universe may be making them on purpose, and one of the most famous black holes in movie history was built on real, peer-reviewed math. Let's get into the strangest real estate in the universe. Start with that world in the Whirlpool, because how we found it is half the story. We cannot see a planet 28 million light-years away. That's absurdly far. Every other known exoplanet sits within a few thousand light-years of us. This one is in a separate galaxy entirely. So astronomers didn't look for the planet, they looked for its shadow. The system, called M51-ULS-1, is a binary. A massive star paired with a compact object, a neutron star or a black hole, that is tearing gas off its companion and superheating it into an X-ray beacon so bright it outshines the sun across all wavelengths by a factor of up to 1,000,000. And the part of that system actually pumping out the X-rays is tiny, roughly the size of a small planet, which means if a planet passes in front of it, it can block the X-rays almost entirely. Using the Chandra X-ray Observatory, researchers caught exactly that. The X-rays from M51-ULS-1 dipped, then vanished completely for a stretch, the full event lasting around 3 hours. The best explanation for a clean, total eclipse like that is a Saturn-sized world transiting the source, orbiting at roughly twice Saturn's distance from our Sun. It's still a candidate. Its huge orbit means it won't pass in front again for decades, so we can't easily confirm it. But it cracked open a brand new way to hunt for planets in other galaxies entirely, not by their starlight, but by the X-ray shadows they cast across a black hole. Now, M51-ULS-1b would have been captured or formed in a binary. But here's where it gets wilder, because physicists think planets might form directly around the giant black holes at the centers of galaxies. They've even coined a name for them: planets. Black hole planets. The logic is unsettlingly simple. How do normal planets form? Around a young star, there's a swirling disk of gas and dust. Dust grains collide, stick, clump, and over time, snowball into planets. Now look at a supermassive black hole. It is also surrounded by an enormous disk of gas and dust, vastly bigger than any disk around a star. And to be clear about the scale of the sun these worlds would orbit, Sagittarius A star, the supermassive black hole at the center of our own galaxy, has the mass of about 4 million suns, yet is so compact that its dark sphere is only around 40% the width of Mercury's orbit. That is the kind of object the planets would circle. 4 million solar masses crushed into a space you could tuck inside the inner solar system. So in 2020, a team led by researchers in Japan ran the numbers and argued that the exact same dust clumping process should happen out there in the cold, dense outer regions of those disks, far enough from the black hole that dust isn't vaporized. Grains collide, they stick, they grow, and given enough time, you don't get 1 or 2 planets. Their work suggested that around a single supermassive black hole, there could be tens of thousands of planets. Some rocky like Earth, but potentially many times larger. Some gas giants. Entire planetary systems with a black hole where the sun should be. We haven't confirmed a single one yet. They'd be hidden deep in the glare and dust. But the physics says they should be out there, possibly by the thousands, right now, circling the dark heart of our own galaxy. And if that sounds too exotic to believe, remember this: nature has already proven it builds planets in places we thought were impossible. The very first exoplanets ever discovered, back in 1992, weren't orbiting a normal star at all. They circled a pulsar. the dead, spinning, radiation-blasting corpse of an exploded star, one of the most lethal environments imaginable. Astronomers were stunned. A supernova remnant is the last place anyone expected to find worlds. Yet, there they were. The lesson burned into astronomy that day was simple and humbling. The universe makes planets almost everywhere, under conditions far harsher than we'd ever guess. So planets forming in the dust around a black hole isn't a wild stretch. It's exactly the kind of thing the cosmos keeps doing the moment we assume it can't. The planet researchers even estimated it might take a few 100 million years for these worlds to grow in the outer disk. Long, but a blink in cosmic time. And forming in place isn't even the only way to end up orbiting a black hole. There's a second route: theft. The center of a galaxy is crowded with stars, and most stars come with planets of their own. Now and then, a star on a long looping orbit swings close to the central black hole. When it does, the black hole's monstrous gravity can rip a planet right off that star, gravitationally pickpocketing it, and capture the world into its own orbit, leaving the parent star to sail on without it. Over the long history of a galaxy, a supermassive black hole could quietly assemble a collection of stolen planets this way, worlds that were born in the warmth of a normal sun and then kidnapped into the dark. So between the planets forming fresh in the disk and the orphans dragged in from passing stars, there may be two completely different populations of planets haunting the galactic center: the native-born and the abducted. Which brings up the question everyone immediately asks: how does anything orbit a black hole without being eaten? And the answer is one of the most beautifully counterintuitive facts in physics. A black hole is not a cosmic vacuum cleaner. It does not suck. Here's the thought experiment physicists use. Imagine you instantly replaced our sun with a black hole of the exact same mass. What happens to Earth's orbit? The answer is nothing. Earth would keep circling on the exact same path, same speed, same year. We'd freeze and die in the dark, yes, because we'd lose the light and heat. But gravitationally, nothing changes at all. Because gravity only cares about mass and distance, not whether the object is a glowing ball of gas or a black hole. The sun isn't holding Earth with light, it's holding it with mass. Swap the mass for a black hole and the leash is identical. A black hole only becomes a death trap if you get extraordinarily close, far closer than any normal orbit. From a safe distance, orbiting a black hole is no more dangerous than orbiting a star. In fact, one astrophysicist calculated that a single black hole could be surrounded by something like 1 million planets in stable orbits, theoretically capable of supporting life. 1 million worlds around the dark. And we don't have to take this on faith, because we are already watching it happen, not with planets, but with whole stars. At the center of our galaxy, a cluster of stars known as the S-stars orbits Sagittarius A star in plain view of our telescopes. The most famous, S2, loops around the black hole once every 16 years on a long ellipse, and astronomers have tracked it for decades. At its closest pass, it dives to within about 17 light hours of the black hole, only about 4 times Neptune's distance from the Sun, and the black hole's gravity slingshots it up to nearly 3% of the speed of light, around 18 million miles per hour, before flinging it back out. It survives every single orbit. Another star in that cluster, the current record holder, whips around at roughly 8% of light speed. These stars are not theory. Their orbits have been measured so precisely that S2's path was used to confirm Einstein's general relativity in one of its most extreme tests ever, and to weigh the black hole at about 4 million suns. The point is simple and staggering. Stable orbits around a black hole are not a hypothesis. We are watching dozens of stars do it right now. If a star can dance that close and live, a planet sitting safely much farther out has no trouble at all. But around the dark raises the real problem, and it's where the movie everyone's thinking about comes in. If your sun is a black hole, where does your warmth and light come from? This is the puzzle at the heart of Interstellar and its famous Miller's Planet, the one where the crew lands and the ocean world with the mountainous waves nearly kills them. That planet was not science fiction hand-waving. The physicist Kip Thorne worked out its real physics, and it's stranger than the film even had time to explain. Miller's planet orbits a giant black hole called Gargantua, and the crew's most gut-wrenching discovery is the time. On that planet, 1 hour equals 7 years back on Earth. That is not a plot device invented for drama. It's general relativity, exactly as Einstein wrote it. The closer you sit to a black hole's immense gravity, the more slowly your time flows relative to everyone far away. To get a time warp that extreme, 1 hour stretching to 7 years, the planet has to be skimming just outside the black hole's point of no return, hovering at the very edge of the abyss. And for a planet to survive an orbit that close without being torn apart, Thorne calculated 2 hard requirements. First, Gargantua has to be supermassive, at least 100 million times the mass of our Sun, because, counterintuitively, the bigger the black hole, the gentler its tidal stretching at the edge. A small black hole would shred the planet instantly, spaghettifying it into a stream of debris. That word, spaghettification, is the real reason size matters, and it's worth understanding because it's the most gruesome physics in the universe. Gravity gets stronger the closer you are. Near a small black hole, the difference in pull between the near side of an object and its far side is enormous. Your feet, if you fell in feet first, would be yanked vastly harder than your head, stretching you into a long, thin strand like cosmic taffy. That's spaghettification, and around a stellar mass black hole, it would tear a planet or a person apart long before they even reached the edge. But here's the twist. The bigger the black hole, the larger and more spread out its boundary, so the difference in gravity from one side of an object to the other becomes gentle. Around a truly supermassive black hole, you could cross the point of no return without feeling yourself stretched at all. This is the strange mercy of giant black holes. They are the only ones forgiving enough to let a planet, or a world full of oceans, orbit right at the brink and stay in one piece. The monsters big enough to host worlds are big enough not to rip them apart. Second, the black hole has to be spinning at very nearly the maximum rate physics allows, which drags the safe orbit close enough to produce that insane time dilation. Get all that right, and yes, you can have a planet there. And those mile-high waves? Real consequence of the physics. The black hole's tidal gravity raises enormous bulges of water, and the planet rocks slightly under that grip, so the bulges sweep across the surface as walls of ocean. It's all consistent. A world at the edge of a black hole where an afternoon costs you a lifetime. Just how close to the edge is that planet? The time dilation on Miller's planet is so severe that in terms of the physics, it's roughly equivalent to the planet moving through space at about 99.9999998% of the speed of light. It is hanging at the absolute brink, a hair's breadth in cosmic terms, from the point where it would fall in and never return. And the film quietly makes a second, smarter point with its other worlds. There's a third planet in the story, Edmund's planet, that barely appears, and it's the one with the best real chance of supporting life, precisely because it sits far from Gargantua. Not so close that time warps and tides rip it apart, not so far that it's a frozen void. The movie's hidden lesson matches the science exactly. The closer you get to the black hole, the more spectacular and the more deadly it becomes. Survival lives in the middle distance. So a planet can be there, it can stay in orbit, but can anything live there with no sun? This is where the real science gets genuinely hopeful in a way that surprised even the researchers. A black hole, strangely, can give a planet light and heat in more than one way. First, that accretion disk, the ring of gas spiraling in, heated by friction to extreme temperatures, glows ferociously. A planet at the right distance could be warmed by the disk the way Earth is warmed by the sun. But there's a second, far weirder source, and it comes from the time dilation itself. A physicist named Jeremy Schnittman worked out that a planet sitting that close to a black hole, with time running so slow, would see the entire outside universe sped up and its light blue-shifted, squeezed to higher energy. The faint, frigid afterglow of the Big Bang, the cosmic microwave background that fills all of space at a chilly couple of degrees above absolute zero, would, from the planet's blue-shifted point of view, be compressed and concentrated until it shines like a warm star. The black hole's gravity would literally turn the cold background radiation of the universe into a usable sun, a world warmed not by a star, but by the squeezed light of the cosmos itself, focused by the very thing trying to swallow it. And yet, before you start packing, there's a brutal catch that makes most of these worlds almost certainly dead. The thing that makes a black hole's disk glow so usefully is the same thing that sterilizes everything near it. As supermassive black holes feed, they blaze as some of the most violent objects in the universe, flooding their surroundings with X-rays and extreme ultraviolet radiation. One study found that this radiation, during a black hole's active feeding phase, could strip the atmosphere clean off an Earth-like planet, boiling away an entire Earth's worth of air, even thousands of light years away from the galactic center, and bathe any exposed surface in enough high-energy radiation to wreck the chemistry life needs. The center of a galaxy, where the planets would swarm thickest, is one of the most hostile places imaginable for biology. The light source and the death sentence are the same object. And this isn't only ancient history. Our own galaxy's black hole, Sagittarius A star, is quiet today, but there's evidence it roared to life in the relatively recent past, with signs of major flare-ups around 6 million years ago, and even a far smaller burst just about a century ago. So the central region of the Milky Way may flicker between calm and lethal over cosmic time, periodically blasting its neighborhood and resetting the clock on any biology trying to get started there. A planet near the galactic core wouldn't just have to survive its strange birth. It would have to weather these recurring storms of radiation every time the giant in the middle decided to feed again. So picture the full, real landscape. A confirmed candidate world casting X-ray shadows across a black hole in another galaxy. Possibly tens of thousands of planets forming right now in the dusty dark around the heart of the Milky Way. Worlds that could sit in stable orbits by the million, perfectly safe from the gravity everyone fears. Warmed impossibly by accretion fire and the blue-shifted echo of the Big Bang, while being scoured by radiation that strips their skies away. Every one of these is built not on fantasy, but on real equations, real telescopes, real peer-reviewed papers. We were taught that a black hole is where everything ends. The universe seems to be quietly suggesting that, for some worlds, it's where they begin.